So thank you very much for coming to our webinar today. We're going to be talking about sample observation, innovations in thermal analysis and calorimetry. We're really excited to do this, and my colleague Megan Fielding is going to be tackling the bulk of it, but I'm just going to give you a brief introduction on C-Therm, who we are, and then kind of the Rigaku products generally. So if this is your first kind of webinar, C-Therm as a company is about simplifying thermal conductivity testing for the materials of tomorrow. And we do that using our flagship product, which is Trident. So you can see here, it's this nice, imposing looking triangle. And we have our 3 sensors. If you were here really early, you would have seen some of those sensors in action and what they do. And it's all about thermal conductivity. But the reason we have this is because we value kind of having choice. And as a part of this, we partner with a lot of third parties, especially in North America, to kind of provide more in-depth material characterization analysis. So part of this kind of selection, there's a method selection guide for thermal conductivity that I'm sure will be dropped in from the moderator, Jacob. You'll see a lot from him today, but part of this kind of toolbox approach is that we also have different partners. So we partner with Metrovid, which is a company that makes dynamic mechanical analyzers in North America. And they are really top of their class, and that's why we're happy to partner with them. Today, the webinar is really going to focus on Rigaku and their thermal analysis products. So Rigaku, as you're going to hear about, is a Japanese company, but in the US, we kind of sell their products. And one of their really unique features is this sample observation. And that's what we've decided to have the webinar on today, kind of show you really what it can do, what the advantages are, and why you'd want to use this and bring this into your lab. So kind of without further ado, I'm just going to stop sharing my slides and invite my colleague, Megan Fielding, to come on. And she's the real expert in this subject. So.
Thanks, John, for that great intro. I'm going to bring up my part of the presentation here. Right, there we go. So as John mentioned, today we're going to be talking about sample observation calorimetry. And as John mentioned, we are partners with Rigaku, a great group out of Japan. It's really top of their class in thermal analysis. So as you can see on screen there, we have 3 instruments in this thermal analysis line, the DSC, the STA, and the TMA. So with today's topic on sample observation, I'm really going to focus on the calorimetry instruments, so the DSC and the STA. The TMA is great also for measuring thermal expansion, but won't be the focus here today. So with that, let's jump into it. Okay, so what is calorimetry? We're really going to start kind of at the beginning here and build the foundation for the rest of this webinar. So calorimetry includes techniques such as DSC, DTA, TGA, and STA. DSC and TGA are techniques that measure the temperature and the energy changes due to the endothermic or exothermic reactions. And you see that on screen there. That's an example of a DTA or a DSC. Additionally, TGA is a method where the sample's change in mass is measured during heating, cooling, or temperature hold. Can be a standalone instrument with TGA, can also be within a combined system like STA. So STA, or simultaneous thermal analysis, is really just a combined system of TGA and DTA or DSC. And with these instruments, a variety of physical properties can be measured. These include heat capacity, which is perhaps the most common request we get, glass transition temperature, enthalpy of transitions, phase changes, thermal stability, and things like that. So if you are familiar with calorimetry, you'll kind of recognize the graph you see there on screen with some endothermic and exothermic peaks. Doesn't give you too much information visually, which is, a bit confusing sometimes. Like, for example, during my schooling in my undergrad, I had a summer internship where I worked with DSC, and I would often see, things like these endothermic and exothermic peaks, and kind of being a bit inexperienced, wonder what is happening to the sample, or what does the sample look like at this point. So these are a couple limitations of calorimetry there, where if you're a bit less experienced maybe, or maybe you're working with novel materials, you're not quite sure what those peaks mean. So we will chat a little bit here about the limitations of calorimetry. As I mentioned, there can be some confusion. What's happening? Is it crystallizing? Is it, curing? Is there a phase change there? You can't see the sample, so you don't really know what shape is the sample, what has the color changed. You kind of just see it as it goes in, and then you see it as it comes out, and you may wonder, what's happening through the bulk of that test. So, another thing that is of concern is you can't really observe the ignition temperature and the fluidity on STA. So, if you keep that in the back of your mind, we're going to go back to that later in this presentation. I'll show a really great example of observing the ignition temperature there. Okay, so how do we go about, getting that information that we can't see with traditional calorimetry? Well, we can use Rigaku sample observation technology. So as you see on screen there, it's available on these two instruments, the STA and the DSC. And these allow you to actually see if there's a change in color and shape of the sample as it's being tested. And the visual information is always going to be linked to the data. So with this Rigaku sample observation capability, a camera is actually installed there in the top of the instrument, and you can see that in the little red circles there. So you can actually monitor the sample both in real time and also after the measurement, either with a video that plays the full test through, or you can take kind of snapshots of the sample at different points on that thermogram there and place it on the data. We can see some details there in the center of the screen about the camera. And in terms of temperature, with the DSC, the camera can be used from -70 to 350 degrees Celsius. And for the STA, can run from room temperature to 1000 C with the camera. Okay. Now we're going to just look at a quick schematic here of the STA system. This is just so you can kind of see how it's integrated into the STA. In the furnace there, you can see that heat insulating material there and the heater bobbin. They both have a window there, so the sample can actually be recorded by the camera through the test. And there's a protective furnace, or a protective tube, sorry, which surrounds the sample that's made of quartz. And you can see just underneath that there's a devitrification prevention unit, prevention plate. This protects the quartz from contamination by the sample off-gassing. As you can imagine, if you're familiar with STA or TGA, you can kind of run the sample through the decomp or the combustion. So there's sometimes off-gassing there. That plate will just prevent the furnace from getting fouled. And you can run this, by the way, in inert gas or air. It's really easy to clean or replace that devitrification plate, so no worries there. Okay. So I'm just going to give a few examples of how the software looks before I get into some applications. So again, if you're familiar with STA, what you see on the left there is typical of any STA. You'll see the TG curve there in green, and in blue, we will see the DTA, or sometimes DSC. But on the right there, we see the sample observation window. So that's going to be a bit newer for some folks. This is where you can see the sample through the entire test run. It's going to kind of play that video through as it goes. And then after the test is run, we can play it back at different speeds. So another way that you can use the software is, as I mentioned, you can take kind of snippets and you can put them along the data there. So you can actually see what's happening at each point on the graph. This is great for maybe a paper if you're publishing and you want to show a little bit more information about the sample. Also great in like a report. Maybe you're a contract testing lab and your client would be interested in actually seeing their sample through the test. Also great for that. Okay, so now I'm actually going to just play through that video of what you saw on the last screen there. This is trehalose dihydrate, by the way, in its dihydrate form, and also the anhydrous form with combustion occurring at the end. So you can use the video there, or you can take snippets and put them on the graph. These pictures are automatically saved as you do the test. Easy to grab them. And we can see the green there is the TG, so it's coming up on a pretty big mass loss as it starts to combust. Okay, so one more way that I just wanted to show you can use the software. So on the left there, you see the sample image at 26 degrees. That's what it looked like when it went in. And then on the right there, that's kind of the playback video. So as you go through the test, you can always be comparing it back to the original. So a few different ways that you can utilize this capability. And with that being said, that's kind of the background that I wanted to go over. And now we're going to jump right into the DSCvesta. So this system is very sensitive, high performance, but really the main thing I want to highlight here is the sample observation. So this system can be run between negative 170 degrees C all the way up to 725 degrees C continuously. Another huge advantage of the system is kind of not having to switch out the furnace. So sample observation can be used on the system between negative 70 and up to 350 degrees Celsius. There's a really nice feature of quick gas substitution, which I will show an application later on in the presentation with some carbon blackened rubber. Very nice feature of this system. It has a very fast cooling rate from 725 C to room temperature in only 8 minutes. That's with the cooling unit attached, which it is in the picture there, as you can see that kind of tube coming out of the system. And there are a couple other options, the auto sample changer. There's some UV radiation capabilities as well. So it's a nice expandable unit with many different options. Okay, and another capability here I just wanted to highlight. As I mentioned, heat capacity is a really common request that we get. So I wanted to highlight the modulated DSC. That's a capability of the DSCvesta, and if you're looking for the heat capacity, I would really recommend this. It allows for really easy separation of the reversible versus the non-reversible heat events. Can be used simultaneously with the sample observation and also with the UV. So really nice feature there. And if you're considering heat capacity, we would definitely recommend. Happy to share more info after if that's of interest. Just put it in the chat box there. Okay, so now I'm just going to get into some applications. This is the thermal behavior of carbamazepine by sample observation DSC. If you remember back in the start of this presentation, this was actually what I used to show when things can be kind of confusing. So we're going to start here. As we go along, we see the sample actually melts, followed by a really quick crystallization. And then as we go along, we see actually a second melt. So, if you're not familiar with the sample type, you may be confused about these two endothermic peaks. Maybe it's a new sample that you're developing and you don't know what's happening with the sample observation there. It's really easy to see. And actually, another thing I'll highlight, it's not on this screen here, or I don't think the presentation, but there is a really nice feature where you can actually measure the sample through the camera as well. Next example here is some azoxyanisole. This video is nicely annotated, so I think I'll let it play through for you. And just again, really showing the value of having the camera and actually seeing how the sample looks at different points on this. And as we can see there, I'll just point out on that image, you can always see the test time and the temperature always correlated on the video. Okay, and then again, just showing how you could present this in either a paper or maybe a report, kind of just showing how the sample changes through the test. Okay, so with that, I'm gonna kind of jump into the STA. So STA is a combined system of TGA and DTA, or or TGA DSC, can be converted to DSC just by calculating the melting peak area with some standard samples. So quite easy to do there. This STA is a really great system. It adopts the horizontal differential triple coil balance. This cancels out the various fluctuations that can be caused, causing TG drift to achieve a highly accurate weight change measurement. So very nice system. There's also sample controlled TG. We've got a few questions about that lately. So this method is equipped as standard, and this is where you can control the rate of the samples, or you can control the heating rate, based on the sample's change in weight. And a few options for different temperature ranges here. The standard model, ambient to 1100 degrees C, high temperature model, ambient to 1500 degrees C, and what I'm really going to focus on today, the sample observation model, which can run from ambient to 1000 degrees C. So we'll get into the applications here for the STA. So we're going to start with a quick application on copper sulfate pentahydrate. As you can see on the left there, we have the initial image, the blue, and then when it's done the ramp and we take it out of the system, it looks like it's gray. It's lost all its color. It's changed quite a bit, but how does it change and when does it change? How do we get from point A to point B? So let's take a look here at the video. So as you can see there, copper sulfate pentahydrate really dehydrates in 3 stages. We can see the 3 different mass loss on the screen there in green. So at first the sample is this pretty blue crystal, but as it dehydrates, the sample turns from kind of blue to lighter blue, as we're seeing right now. So there's the first mass loss. And then as we're approaching the second mass loss here, we'll see it change to kind of a gray color. So we can see a 14% approximately mass loss in the first and second jumps there. That can be correlated to the 2 molecules that are released. And then as we approach the third mass loss there, we see about a 7% mass loss. And that's due to the single remaining water molecule there. It'll be released in the third mass loss. So this is just a good application to show kind of, how did we get from the start to the end? We can see in this sample observation each of the mass loss and how the sample changes during these mass loss. And we're approaching the last one now here. There we go. And now we can see how the sample has changed during the whole test. And still running. By the way, these video playbacks can be changed to different speeds. Probably could have sped that one up a little bit. But anyway, here is the graph with the kind of snippets of how the sample looks at different points. Next, we are going to go into a really exciting application highlight, with carbon black in rubber. So we can see here on the graph that, there are a couple different mass losses before we change from nitrogen to air. So we performed this in an inert atmosphere. It was nitrogen actually, up to 800 degrees C. And then as you can see, we held it isotherm at 800 degrees C. And during that time, we switched from nitrogen to air, a really quick switch. So if you remember, I mentioned this was a kind of accessory you can get with the system, this gas changer. This is a really great application showing how that is used. So I'm gonna play the video through for you here. So as I mentioned, we see 2 major mass losses here before we switch from nitrogen to air. The first one can be correlated to the decomposition of the resin here in the rubber material, and that's what we're starting to see now, about 47%. You see the sample here kind of gradually getting a bit smaller, and this would be would be a great application kind of to use the sample measuring tool you can do through the sample observation software. Now we're approaching the second mass loss, the decarboxylation of the calcium carbonate. So that would be the filler material. And as we approach 800 degrees C, we're going to hold at isotherm, and then we're going to do a very quick switch from nitrogen to air. The reason we're doing this switch is to see the exothermic peak due to the combustion of the carbon black. And here we go, we see the carbon black has combusted, and we can see from the mass loss there, the amount of carbon black in rubber is about 23%. Really nice application there. The next application we have is a biodegradable polymer sample. Now, this is also a really great one I like to show when kind of justifying why you would need sample observation. With the world kind of turning away from plastics and looking for alternatives, there are a lot of new biopolymers being developed. And we might not necessarily know when things are going to happen, what temperature points, when's it going to melt, when's it going to decompose, that kind of stuff. So let's take a look here at this PHBH straw. So as you can see, there is a little tiny heat event there annotated, the first one at about 150 degrees C. If it was not annotated, it would be very difficult to determine that that's a heat event. So just keep your eye on that first heat event there, which, back in my days of working with DSC, I might have just considered noise. But with the sample observation camera, as you could see there, it was actually the melting point. So that would have been very difficult to determine without sample observation. And we see just about 100% mass loss by the end of this test here. Okay, and this application here, this is an application on solar cells that I threw in. The reason I threw this in was just to show that the STA can be coupled with evolved gas analysis. In this case, it's MS, can be FTIR. So in this case, this is a lead methyl ammonium iodide, an intensifying agent, measured with the STA coupled with MS. So the powder was heated at 10 degrees C per minute from room temperature up to 350 degrees C in a helium atmosphere. And electron ionization was used in the MS ionization mode here. So as you can see with the sample observation, the image on the left is before the mass loss. You can see it's black initially, but after the mass loss, we can look at the image and it is now red. So the gas evolved during the mass loss was determined to be hydrogen iodide, iodine, and methylamine. So another nice kind of additional application, a bit outside of today's scope, but STA can be used in couple with evolved gas analysis. Okay, so now we are going to go into an example of measuring the ignition temperature. If you remember previously in this webinar at the beginning, I mentioned that it is really hard to determine the ignition temperature with traditional calorimetry. So I'm going to let this video play through here for you and show you how we can determine the ignition temperature. And again, the green there is the TG or the TGA mass loss, and the blue there is the DTA. Coming up on the first peak. And the second there. So that happened pretty fast. So let's slow that down a little bit and take a closer look. Okay, so with that slower playback, we were able to see that really sudden firing that occurred in the sample. Now, you may be wondering, how do we get the exact temperature from that? It was really fast in the video. We'll go into it here. This application came from our partners Rigaku in Japan. So please excuse the Japanese software. But it does show how simple it is to determine the ignition temperature. So I wanted to keep this in here. So here we're just going to select the range that we want to analyze. We're just going to pick right around that firing temperature. And we can now pick the exact image where the sample was ignited. And based on all that information there, you can see they get the time, temperature, the TG, and the DTA values. And we can determine that this happened at 295 degrees Celsius. So very nice application there on value of sample observation for ignition temperature. So that actually brings me here to the end of the sample observation portion of the presentation. I'm just going to do a very quick slide on the TMA. Not really a focus for today's webinar, as it doesn't have sample observation, but in case you're interested in thermal expansion or related properties, CTE, just going to give a quick intro of this system. It is actually the only differential TMA available on the market. We did a whole separate webinar actually on the principles of operation, some application notes. I see Jacob has put it in the chat already. If you're looking for thermal expansion, definitely check that out. Gives a great background of the system. Really, really good for low expansion materials like metals and even invars due to its differential nature. So really recommend that. Has a great temperature range, can actually, in its full temperature range, go from negative 150 C all the way to 1500 degrees C. So that would be the high temperature model there with a cooling unit on it. Really nice temperature range, great system for thermal expansion if that's a priority for you this year. And just a quick slide showing these instruments are all really complementary. They work really well together. On the screen, you see a measurement of a PET sample with all three instruments, STA, DSC, and TMA. It's really nice sometimes to correlate the dimensional changes to the heat events and to the mass loss. It really gives you a full picture of the sample and how it's behaving as it's heated up or cooled. So as you can see there, you can see the glass transition. You can see a few peaks on the DTA, DSC. It just gives you a really nice full picture of what's happening to your sample. And this is all done, by the way, in one software, really easy to analyze, overlay samples. There's even some automated data analysis you can set up. So really easy to use software. And all instruments, up to 8 instruments, I should say, can be controlled with one computer. So one computer, save on space. It's all in the same software. It's really easy to analyze the data and overlay. So a bit of a space saver and makes it quite easy. So that is kind of the bulk of the presentation I have for today. Just to summarize, sample observation makes it really easy to see changes in color and shape of the sample. There's no need to guess what's happening at each peak, endothermic and exothermic peak. And a really big one is you can differentiate noise from heat events. Such as that melt, if you remember in the PHBH application there, the biopolymer, it would have been really hard to determine that was a melting point without the sample observation. I know back in my DSC days, I probably would have just discarded that for noise. So a really great system, highly recommend for any lab, but especially academic labs where maybe a lot of students are coming through and maybe not maybe they're not as confident with the method. Really helpful for those labs. Thank you very much for watching this webinar today. Appreciate your time. If you have any questions, please leave them in the chat box there. We'll maybe have time for a few questions at the end of this webinar. My contact information is also on screen. Feel free to send me an email, connect on LinkedIn. Alternatively, if it's easier, just send an email to rigaku@ctherm.com. And with that, I will stop my video here. Oops, stop my video here. And then invite my colleague John back on screen for just a few closing remarks before we get on to the Q&A.
That was a great presentation, Megan. Thank you. We're just going to do a really short outro, just kind of let you know what the month looks like before we get into the Q&A section. But if you want any additional resources, there's plenty of different webinars, lots of previous Rigaku ones as well on calorimetry or TA or STA that Jacob's been dropping in, but all of them would be available at C-Therm's website. So there's the webinars and then tech library, lots of different papers primarily focused on thermal conductivity, but also plenty of papers on the Rigaku's site if Jacob drops that in, relating back to all the different thermal analysis units. A couple of events that are coming up. We will be at, so Megan actually will be at IME West in Anaheim, California. It's February 7th to 9th. So if any of you happen to be in the area, please reach out and see if we can kind of set up any kind of meeting or a conversation, anything like that would be great. And we'll also have some people in the thermal management for EV and HEV over in Germany near the end of February. So really exciting to get back out there after kind of the holiday season. And if any of you are going to be in the area, please reach out. As for upcoming webinars, we have one next week, next Thursday, on importance of thermal comfort in bedding. So a slightly different idea, but still all about kind of the thermal analysis and particularly thermal conductivity in textiles. So that'd be great. Some guest speakers for that as well. Like Megan mentioned earlier, we're always available on LinkedIn, very active there. So you can reach out to Megan individually, or you can follow C-Therm on LinkedIn. Plenty of kind of Rigaku updates there. And that's definitely where we promote our new webinars as well, beyond just this. So it's a really great resource. And then next steps, you can book a video demo, especially for Trident things, and a discovery call to learn about, if sample observations kind of right for you to bring in-house. And you can request a quote as well on the Rigaku website, or just in the chat here, or in an email to any of the emails we mentioned before. And with that, I think I'd like to just say thank you, and we'll move into the Q&A. I'll stop the recording just so that you can feel free to ask your questions. But if you drop off here, thank you very much for joining us, and we hope to see you again at the next one. Thank you.